So, we were talking about different methods of measurement of migration, and we saw that some of these measure parameters which basically relate to the conductivity or the resistivity of the concrete. So, there is a simple test called 4 probe resistivity test, which has the advantage of being portable enough to be carried out on site directly. We also looked at the most common test which is used for durability considerations, that is a rapid chloride permeability test, which is based on an ASTM standard and is widely adopted in most countries. Again, the basic emphasis that you need to give on this is that most of the parameters that you get out of these durability tests are not quantitative parameters, they are qualitative. So, they need to be characterized qualitatively. Okay? You do not really get a quantitative estimate of the ability of chlorides to pass through the concrete, you get a qualitative estimate of whether the concrete is good or not. Okay. Now, there is another test which is more widely being accepted nowadays, it is called the accelerated chloride migration test or rapid migration test, sometimes it is called an RMT, rapid migration test. Now, here the principle is still similar to what you have with the rapid chloride permeability test RCPT, except the difference is here you have the specimen which is sitting inside this big container, this big water bath as you see in this picture here, and this water bath is filled up with the catholite solution. What is the catholite solution? Sodium hydroxide or chloride? Cathodic electrode has sodium chloride solution, because the chloride has to move towards the anode, the positively charged electrode. So, this is the sodium chloride solution. The reason that you place your entire sample container inside sodium chloride solution of such a large volume is that when you have a large volume of the solution, the heating of the specimen is almost negligible. Okay, in the previous case you saw that the solution amount was equal on both sides, chloride and hydroxide were almost equal on both sides, but in the case of migration test the chloride solution is available in a very large volume. So, because of that you have less chance of heating up of the specimen. So, what you do here is again the same, you apply a potential difference between the electrodes, okay, and you make the chlorides drive through the concrete to the other side where you have your anolyte, which is sodium hydroxide. So, anolyte is your sodium hydroxide, catholite is sodium chloride. The one difference here is that for different types of concrete you choose different voltages at which the test is to be conducted. Okay. So, if you choose a concrete which is poor in quality, so how do you choose that? You basically do an initial test to determine the amount of charge that is passing through the concrete, measure the current passing through the concrete and base your voltage for this test based on how much current is passing through. So, if a concrete is poor, it passes a lot of current through it. So, then you choose a lower starting voltage. So, the starting voltage can vary between 15 and 60 volts, you can apply different voltages to the concrete. Now, of course, what you need to do is apply it for a certain period of time to ensure that the same amount of charge is passing through. Okay. So, if you apply a lower voltage, you need to conduct the test for a longer duration of time. If you apply a higher voltage, you need to conduct the test for a shorter duration of time. Nevertheless, at the end of the test, what you do is you split the specimen, you have cylindrical slices the same type as you had in RCPT, 100 millimeter diameter and 50 millimeter thick slice, and this is split open and then you spray silver nitrate on the split surface. So, what will silver nitrate do? It reacts with chlorides to form silver chloride, which is white in color, right. So, you actually get to see the depth of chloride penetration directly from your specimen. Okay. So, you can actually measure the depth of chloride penetration directly from your specimen. So, that is the advantage here, that you actually get some inkling of how much chloride can actually go through, but still please remember this chloride is still getting driven through because of potential difference, it is not driving because of diffusion. Diffusion can never happen so quickly, it takes months to happen. So, this is a case of chloride getting migrated, but nevertheless you are actually measuring the chloride migration by looking at the depth of chloride penetration, and using the Nernst-Planck equation that we talked about earlier, you can convert this chloride depth into the migration coefficient, which is basically an equivalent of the diffusion coefficient, not the same, but an equivalent of the diffusion coefficient. It is called migration coefficient, and that again people have suggested, researchers have suggested classifications based on the values of the migration coefficient for a qualitative classification of the concrete. Now, one thing you need to understand is in RCPT we got an idea about the charge that is passing, and I told you that that is not really a quantitative parameter that can be linked to the design of the concrete. However, in this case you get actually a migration coefficient. If you utilize the relationships that were similar to the Fick's second law, where we look at the non-steady state diffusion, you can relate this migration to the diffusion coefficient that you find in Fick's second law and then try to model this process. Okay. So, you can actually use this migration coefficient as a quantitative parameter in models that predict the service life of the concrete. Indeed, the European model, which is called Duracrete, looks at the use of this migration coefficient value to determine the service life of your concrete structures. Okay. So, this is probably a more useful test as opposed to the RCPT test to obtain the result which can be quantitatively utilized. The only problem is this test takes much longer than the RCPT depending upon the type of your concrete. So, you may actually have to wait a much longer time to get a reasonable result. Okay. RCPT again, because of familiarity, because of the way that people have been exposed to it. Again, remember I told you that the silica fume manufacturers were one of the primary reasons that RCPT got promoted in a big way, because silica fume concretes were showing really excellent results with RCPT. So, for a long time that was the only durability test that was actually being conducted. Only in the last 10 to 15 years the debate on use of appropriate durability tests has been rekindled, and people have started talking about additional tests that can actually be done along with RCPT to really get a better estimate of concrete durability. The other variant of this migration test is called a chloride conductivity test. Now, what was happening in the previous two investigations, that is the chloride permeability as well as chloride migration test, was the fact that your chloride and hydroxide presented two different media on each side of your concrete specimen. So, that means there are multiple reaction mechanisms that are involved or transport mechanisms that are involved. Not only is the migration causing the chloride ions to move, there is also possibility of chloride diffusion, there is a possibility of movement of other ionic species and so on and so forth. Okay. So, what the South Africans did was they took the test for what it intended to convey. What does it convey primarily? The conductivity of the concrete. That is what is being conveyed in most of these experiments. The higher the conductivity, the less the durability of the concrete. So, the South Africans modified this test to simply measure the conductivity, and to ensure that this conductivity was not being driven by either migration or by diffusion of the chloride ions, what they did was both the anolyte and the catholyte solutions were made to be sodium chloride, and on top of that the specimen itself was vacuum saturated in a sodium chloride solution. So, what happens here? When you vacuum saturate specimen in sodium chloride solution, it is already filled up with chloride. So, all the pores are filled with chloride again. So, there is no way that the chloride from here would like to move to the other side, because first of all concentrations are equal and the sample is also saturated with the chloride solution. So, what you are doing is simply applying a current across the outer electrodes and measuring the voltage across the concrete specimen. The inner electrodes are connected directly to the concrete specimen by the help of these capillaries called Lugin capillaries. So, you apply this power source is applying a current on the outer electrode, and you are simply measuring the voltage across the concrete, and you convert this voltage to the conductivity of the concrete. So, you find inverse of resistivity and call it conductivity, and based on the concrete conductivity you can again qualify the concrete in terms of being very good or poor or very poor. Okay. Again, qualitative classification. Conductivity does not have any significance in directly associating itself with any service life parameter. Okay. Now, we are talking a lot about service life, but we will actually look at it only when we get to corrosion. Okay. But right now what I am just trying to tell you is this: these values are not directly utilized in any service life prediction model. They are just qualitative classifications of the type of concrete that you have in your system. So, again I was talking about this South African National Roads Agency. So, they are implementing durability specifications in their projects by calling upon the contractor to actually build mock-up panels or mock-up slabs along with the other regular concrete specimens, or not specimens, along with the regular concrete structure, which are subjected to the same curing conditions and site conditions as the actual concrete structure. Then from time to time they need to pull out core specimens from these slabs or mock-up panels, test the durability of that, and the durability is tested by three methods. One is chloride conductivity, the other is oxygen permeability, and the third is water sorptivity. So, in all three methods the concrete has to satisfy certain minimum characteristics. So, what they are doing is using these durability parameters to tightly control the quality of concrete that is being achieved in their projects. and the roads agency has been implementing this for nearly 10 years now, or more than 10 years now, and they have had very good success with it. Okay. The only difficulty lies in actually establishing where they can do the test, because the laboratories where the test can be done has to have a proper working system. For example, the oxygen permeability cell has to be properly calibrated, the chloride conductivity apparatus has to be properly done, and so on. Water sorptivity, you do not really need anything other than a balance, so it is not that difficult anyway, but vacuum saturation has to be done for the specimen, so that is something different. So, when all these tests are done, you need to ascertain that the labs which are doing the tests have the required equipment as well as are calibrated to do these tests accurately. So, they actually have an audit team from the South Africa National Roads Agency Limited, which goes and audits the labs to check whether all these systems are well in place. Only if they are qualified, they can take up the testing of these specimens. So, this is a very good example of how the state authorities have actually been influenced by the academic research to implement the durability specifications directly in their construction, and they have been quite successful with it. Now, there was a study that done there by one of the research scholars at University of Cape Town, and that found that using these projects they were able to bring down the variability in concrete tremendously, and the variability was almost non-existent, especially in the case of a precast concrete production. Now, in precast obviously we know the quality is much better controlled, so they actually could see that difference very clearly from regular concrete construction to precast concrete construction. The quality difference clearly manifested itself in the durability values that were obtained. So, again this is an example that can be emulated in our country also. We also have several highway projects which are being currently executed. We have a lot of metro specifications that are currently being written, and it all requires a little bit of willingness on the part of the owners to try out these systems, because ultimately they are guaranteed a much better quality of the construction if they implement these systems properly. But for that they need to go the whole hog. They need to understand that all this has to be pre-planned, the concrete mix design also has to be done with sufficient amount of time, and to ensure that they get the kind of quality that they have. Okay. Because first of all, the awareness of durability testing in our country is quite limited. Not many people know much about durability tests. Increasingly, as more number of consultants from abroad are taking part in joint ventures in India in different construction projects, there is a lot more awareness of durability testing that is slowly creeping in. If you go to any major project, for example, most of the airports that were expanded, they were done not by just an Indian company, but they had to have a joint venture with a company that had executed airports of similar types abroad. So, in most of these projects you had people from external conditions who had actually been exposed to durability related specifications previously in their construction projects. So, these days you are increasingly seeing an infiltration of more and more durability tests in our construction projects, but it will only increase in the near future. But for that, to be ready for that, we also need to understand what are these durability tests actually telling us, what kind of what are these results conveying with respect to the quality of the concrete. Are we accurately testing what we want to test in that given environment or not? So, for that the basic background knowledge that I talked about in this entire chapter is very essential. Okay. So, just to summarize the durability test methods and parameters, there are set of durability test methods that address chloride penetration, and here we are looking at migration based tests or diffusion based tests. So, you have the RCPT, accelerated chloride migration, chloride conductivity and bulk diffusion, and again the parameters that they are giving could be quite different. In this case it is a total charge passed, in this case it is actually a diffusion coefficient, non-steady state diffusion coefficient or migration coefficient. In chloride conductivity test you actually get simply the conductivity of the specimen, and here you get the concentration profile that can again be fitted into a model to obtain the diffusion coefficient, the apparent diffusion coefficient. Okay. So, if you look at the models, they make use of this. The Duracrete model from Europe makes use of chloride migration coefficient, and the Life 365 model, about which we will talk about in the corrosion chapter, makes use of the apparent diffusion coefficient from chloride diffusion tests directly into the prediction of service life. Now, added to this you have gas penetrability measurements using oxygen permeability, air permeability or accelerated carbonation, and then you also have water permeability tests that look at sorptivity or surface permeability or penetration depth of the water itself. And then there is an indirect method that measures the concrete resistivity directly, that is called the concrete resistivity method, resistivity is not really giving you an indication of any of these three characteristics, it is a combination of all the factors. It basically reflects the interconnectivity of the porosity that you have in your system. This table simply again summarizes all the transport mechanisms in concrete and the relevant test methods, and this is a very good guideline to have to think about what test methods you need to prescribe for a specific service environment. Okay. So, you have this option which is basically capillary action. So, this is represented by the sorptivity test method. Again another example, Wick action is transport of ions or water from a phase in contact with water to a drying phase, that again is reflected quite nicely with the sorptivity test. Now, bulk intake of water by absorption is not necessarily related to sorptivity, you could also do water absorption test directly, but the sorptivity test, if you look at the details of the sorptivity test, the last step in that test is to actually completely vacuum saturate the concrete. So, actually measure the actual absorption also apart from the sorptivity rate. So, but if you want to directly measure water absorption, that is also possible. So, based upon the type of environmental condition you have, you establish first what are the mechanisms that are likely to be acting in that region and what are the test methods that you need to look at. To give you an example, I have picked up the example of a concrete column in a marine environment. You know that the concrete column in a marine environment is probably the most difficult condition for concrete to perform itself, to perform service in. So, you have three different zones within a marine environment. You have a zone which is completely submerged, where the water level is always above that level, so that you have a complete submersion. The concrete here in this region is subjected primarily to chemical attack because of the chemicals present in the seawater, and there is also water pressure. So, there will be driving water inside by by permeation. So, you have permeation, and then what is the second mechanism you will have? Since there are chemicals outside, ionic species outside will start diffusing into the system. So, you have permeation and diffusion as the primary mechanisms that are driving the performance of concrete in a submerged condition. Now, you have the atmospheric zone which is on top, okay, which is not really subjected to a direct influence of the water, but there will still be some salt spray that will be spraying onto that. Okay. So, it is not directly in touch with the water, but there will be salt spray. So, there will be drying and wetting. So, what sort of mechanism will act there? Sorption, there will be sorption, definitely sorption will be there. What else will happen? There will be Wick action because there is extreme drying happening on top, right, and to some extent there will also be diffusion. To some extent there will also be diffusion. If the chlorides are deposited on the surface, slowly they will diffuse into the concrete. Only thing that will depend entirely on whether that concrete is in a saturated condition or unsaturated. If it is unsaturated, there is no question of diffusion. Only when it is saturated you get diffusion. Now, the main zone to worry about in seawater is this zone which is directly exposed to the splashing of the waves, as well as the zone which is exposed to the tidal action. So, in high tide there is wetting, and in low tide there is going to be drying. Okay. So, again all the mechanisms that we talked about, whether in the submerged condition or atmospheric zone, all of those come together in the splash zone, in the tidal zone. So, you have diffusion, you have water permeation, you have Wick action, you have sorption, you also have physical degradation because your waves are splashing against the concrete. So, there is physical degradation. So, that is probably the most extreme condition that you want to design for. So, based on that you can then list out the mechanisms that are actually acting in these regions, and for that you need to actually specify the test methods. Now, we will connect this again with the actual classification, how we can use different test methods to specifically address these issues in a later chapter, but right now this is what I wanted to tell you, that for a particular service environment you need to work out the kind of transport mechanisms that will be prevalent and then address that by suitable durability tests that we saw in the previous slide. Okay. So, that is how you do a durability design for a concrete structure. Assess the environment first, identify transport mechanisms, prescribe test methods, but there is one very important step that we have not covered here, is for those test methods what are the limiting values of the durability parameters. I showed you some examples previously from performance specifications where people said 600 coulombs, 1000 coulombs and so on, but is that reflecting anything about the service life of the concrete? Probably not. It is more a way of controlling the quality of concrete, and indeed research from around the world has shown that if you specify a durability test in addition to strength test, the quality of the concrete ends up being much better in the long term. Okay. So, right now durability tests are being used for qualitatively characterizing the concrete to ensure the quality is maintained during the construction project, But what we want to do further is to utilize these durability parameters to actually predict how long it will take for corrosion to initiate in the system. So, we will look at how this can be done to some extent in a later chapter. Okay, with that we come to the end of the chapter on durability. There are a lot of papers in this subject. I have only selected a few where we have directly provided our inputs also. So, there is a lot of research on this has happened in our laboratory, primarily with the research project that we were involved in with Lafarge, which is one of the largest construction material manufacturing companies. And we did this research over a period of 4 to 5 years, and we produced a lot of data based on this research, which talks about how these tests can be utilized and what we can do with the values we get, the kind of durability parameters that we obtain from these tests. What do they signify for the performance of the concrete? Okay, so this chapter is on chemical attack, which is one of the primary causes of durability related issues in concrete. There are many types of chemicals that can attack concrete, and in the last chapter we saw how different kinds of transport mechanisms can drive these chemicals into the concrete system. But one factor that is controlling all the chemical attacks or any durability problem in concrete, as we saw in the last chapter, is the interconnectivity of the porosity in concrete or the permeability of the concrete. So, the primary factor that controls most durability problems is permeability. So, you will see in this chapter and in the chapter that follows that the primary mechanism of protection of concrete will still be based on production of concrete with low permeability, and that is how you will obtain a better quality concrete that will resist most of the durability problems. But in this chapter we will try to look at what are the mechanisms of different types of chemical attack and how we can actually devise strategies for protection other than the fact that we can produce concrete with low permeability. That is something which will be a common strain in all the durability investigations that we talk about. So, there are different types of chemical attack, the most common ones being sulfate attack, acid attack, chloride attack and carbonation. Okay. So, let us look at these in more detail. First, sulfate attack happens whenever there are sources of sulfates present in the groundwater or in the soil, and generally when the sulfates are getting driven from an external environment into the concrete, we call it external sulfate attack. But there are some conditions under which we can actually have the kind of symptoms that are shown by external sulfate attack happening from within the concrete. That means the source of the sulfate which is leading to deterioration is within the concrete, and that is called internal sulfate attack or delayed ettringite formation. So, we know that ettringite forms in the early stages of cement hydration and slowly converts to the monosulfate phase. If there is more sulfate available towards the end, this ettringite will reform because the monosulfate is combining with sulfate to form trisulfate, which is ettringite. Okay. So, this reformation of ettringite is what causes the problems, because we have discussed earlier that ettringite can be expansive based on the type of crystal habit that it actually forms, and in normal sulfate attack also this ettringite formation happens in the hardened concrete, and to protect against that we use what? What type of cement do we use to protect against ettringite formation? Sulfate resistant cement, right. We use sulfate resistant cement which is low in C3A, tricalcium aluminate, because if you have more C3A, the tendency is to stabilize the formation of monosulfate. So, that monosulfate can reconvert to ettringite in the hardened concrete, but when you have low C3A, the tendency is to stabilize the ettringite at the early stages. So, you do not have formation of later ettringite. So, although we call this internal sulfate attack as DEF, delayed ettringite formation, even in external sulfate attack the primary cause of failure is the expansion caused because of secondary ettringite formation. That means the ettringite that is not forming at the early stages, that is forming at the later stages. Okay. Early stage ettringite is called primary ettringite, the ettringite that forms later is called secondary ettringite. The common chemicals that carry sulfate ions include sodium sulfate, magnesium sulfate, calcium sulfate, ammonium sulfate, iron sulfate. What are some sources of pollutants which carry sulfates? Soil has, obviously, agricultural effluents can have sulfates from the fertilizers, right. So, these are active sulfate based chemicals which are in there in the soil, but what you need to understand is not all of them are soluble to the same extent. For example, if you look at sodium or magnesium sulfate, the extent of solubility is much greater as compared to calcium sulfate. The most abundant sulfate in the soil is calcium sulfate, but the solubility of calcium sulfate is limited, whereas you have much greater solubilities for all the other types of sulfates, including sodium, magnesium, ammonium or iron. Now, why is that important? Why is the solubility important? Only if they are soluble, they can actually penetrate the concrete either by diffusion or by permeation, right. So, getting into the concrete by the sulphate is only possible when you have soluble sulphates present in the soil. So, the groundwater will dissolve these sulphates and bring it to the concrete surface, and then the sulphates will penetrate either based on diffusion or a combined diffusion permeation mechanism, right. So, now what you need to worry about is not just the amount of sulphate in the soil, but how much of this is present in a soluble form. But I will also tell you one more thing that you need to be very careful about is the cation that is associated with the sulphate. Primarily we need to worry about magnesium and ammonium as cations. We will discuss why that happens later, because mostly the cationic species which are associated with the sulphates, if they are of a type that lead to an acidic reaction in the cement paste, then they are highly disastrous. For example, magnesium and ammonium can really cause a lot more problems in your cement paste as opposed to sodium or iron or calcium. Okay. So, when we are looking at magnesium, particularly magnesium attack, we need to be extremely careful about the role of the magnesium ion in the solution also. So, not only we need to worry about sulphate, we also need to worry about the cation. So, cationic damage with magnesium especially is very important. We will talk about how that happens in just a minute. Now, there are other forms of sulphate attack also. We have talked about external sulphate attack, internal sulphate attack, primarily related to ettringite formation, but then you can also get salt crystallization. If you have drying and wetting, the salts that are getting deposited by the water in the porosity, after the water dries out, these salts start crystallizing. Again, this can happen because of sorption, wick action, all those kinds of things can make this problem even worse, because of which you have salt crystallization. And this crystallization happening in fine porosity of concrete can create crystallization pressures, and that pressure will break open the concrete. So, again you have salt crystallization damage. The other damage which is getting more and more important these days is called thaumasite attack. Now, thaumasite is a phase that forms when, apart from sulphate, you also have a source of carbonate inside the system. Okay. So, you form a calcium silicate sulphate carbonate. Okay. It is a very complicated product that actually forms because there is source of carbonate available in the system. Where is this carbonate coming from? Limestone. Yeah, a lot of limestone is being used in the concrete these days. So, especially when you have low temperature conditions, less than 15 degrees, you can have a lot of chances of thaumasite forming, and this thaumasite attack actually happens directly on the CSH. So, you convert CSH into thaumasite, which is your calcium silicate sulphate carbonate. Okay. Complicated formula, but essentially the CSH is getting converted into thaumasite, and this thaumasite has absolutely no binding strength whatsoever, and it turns your concrete completely into mush. So, there have been instances where this has been detected as the cause of damage. In the early days, people were not able to distinguish thaumasite from ettringite because both of them look quite similar as far as the X-ray peaks were concerned, but later people started looking at these mechanisms and looking at the influence of carbonate in these mechanisms. So, when you have carbonate sources available, you do have a chance of forming this material thaumasite, which leads to a lot more destruction as opposed to simple sulphate attack. Well, I would not say that this reaction does not happen at higher temperature. There have been evidences of thaumasite formation even at higher temperature, when you are talking about 20 to 25 degrees Celsius, but the chances are less that thaumasite would form at that temperature, and sometimes they are formed without any carbonate sources in your aggregate also. Why does that happen? Because there is some amount of CO2 dissolved in water, especially from outside. If you have seawater especially, will have lot more carbon dioxide dissolved. So, you can get thaumasite formation in those conditions. Now, what are the reactions of sulphate attack? Let us look at these in a little bit more detail. You have hydrated cement phases that react in an aqueous phase with the sulphate ions. So, what are the hydrated cement phases that will react? Monosulphate. What about calcium hydroxide? Will it not react? Calcium hydroxide also will react. When calcium hydroxide reacts with sulphate, what is the product you should form? Calcium sulphate or gypsum. Okay, you start precipitating gypsum, and remember the original cement reactions. The gypsum goes into reaction with C3A to form ettringite. So, you have the remnants of C3A and tricalcium aluminate hydrates along with monosulphate that can then react with this gypsum to reform ettringite. So, gypsum forms first and then combines with the aluminate sources to form. So, again gypsum formation itself has been associated with some level of damage, primarily because gypsum is much softer than CSH or calcium hydroxide for that matter. Okay. And ettringite formation primarily causes expansion that leads to damage in the matrix. Once these reactions almost near completion, you have another type of reaction that may happen is the progressive loss of stability of CSH. Now, why do you think CSH becomes unstable? When would CSH become unstable? When the pH of the surrounding system reduces. So, if you are consuming calcium hydroxide, when your calcium hydroxide goes down, your resultant pH also will go down, and this is where the role of the cation is very important. Certain cations, for example, like sodium, okay, if you have a sodium sulfate reacting with calcium hydroxide, what will you get? Gypsum plus sodium sulfate plus calcium hydroxide should give gypsum plus sodium hydroxide. So, we are not really changing the basicity of the system much, because we are again forming a highly alkaline material. Okay. You are depositing a salt, but you are also forming an alkaline system around it. So, the CSH does not get really unstable in sodium sulfate solution. Now, when you have magnesium sulfate attack, MgSO4 plus CaOH twice will give you CaSO4 gypsum plus magnesium hydroxide. Now, this magnesium hydroxide is an insoluble solid, and when that forms, it drives more and more of the calcium hydroxide to get removed from the system. I will show you the example of how that happens, and that leads to a major reduction in pH, and when that pH reduction happens, this will become a reality, and that is when your concrete will get really broken down tremendously. It is not because of gypsum and ettringite that concrete fails in a major way. Primarily, it is because of this fact that your CSH is losing its stability in an acidic system, or not acidic, less alkaline system. Okay. So, let us look at the reactions in more detail. Again, please remember the sulfate should be written with a bar on top. For convenience, I have used bar at the bottom or underlined letters at the bottom. I did not have an equation editor at that time, so I just prepared it like this. So, your calcium hydroxide plus sodium sulfate, of course, there is water associated in this reaction. Without water, this reaction does not happen. You have gypsum, CsH2 and sodium hydroxide. In second case, you get gypsum and magnesium hydroxide, which is also known as brucite. Now, this brucite is the insoluble solid that actually forms a layer on the surface of the concrete. Now, you may wonder that if you are forming a layer, insoluble layer on the surface, it must be protecting your concrete from further damage. Indeed, that is what happens in the early stages of magnesium sulfate attack, and after this layer actually forms on the surface, you get some respite from the further penetration of the sulfate solution. But please remember, when you form this layer, you are causing this reaction to keep on happening. So, that has been more and more of calcium hydroxide will keep getting consumed, and at a given stage, the sulfate reactions just underneath this layer may be creating expansions that are large enough to break this layer, because you are only forming a surface skin, right, and this layer will eventually break, and when it breaks, already the concrete is very poor inside, more sulfate gets in, you start reprecipitating other phases. So, this layer will afford protection only to a certain period of time. Okay. Unfortunately, we do not have a clear measure as to what is that time frame up to which it will afford protection. It is a very complicated mechanism. It is still debated by several people as to whether we can look at mineral admixtures positively or not. We will look at that in just a minute. I will show you the results. So, the formation of brucite protects the concrete from further attack in the initial stages, but it does not help in the long run. Now, the CSH, especially when you have cations like magnesium present, can react directly with your magnesium sulfate and lead to the precipitation of gypsum again, magnesium hydroxide or brucite, and a silica hydrate. That means your calcium from CSH is getting removed. Now, why is this happening? I told you that calcium hydroxide is getting consumed, that means the quantity of CH is going down. To maintain a balance or to maintain a pH balance, what the CSH does is it gives out calcium to the surrounding system to maintain the balance, okay, to maintain its stability. So, what is happening to the calcium to silica ratio? It is progressively going down in the CSH. At a given point, the amount of attack is so much that all the calcium has actually gone out of the system and you form a silica hydrate. If you look at any acid attack, the silica hydrate formation is quite similar. So, this is what is called leaching, calcium leaching. Now, what I have not told you about is, even if you have a pure source of water, pure water, distilled water, it can actually lead to calcium leaching in your system. But of course, the effect is not going to be as disastrous as magnesium sulfate attack, but it is slowly but surely going to cause calcium leaching from your system. That is why when we cure concrete in the laboratory, if we cure it under water in just plain water tank, we are going to have calcium leaching in the system. Okay. But if we cure it in a moist room where there is fog bringing moisture to the system, it is not going to happen like that. Or alternatively, for laboratory purposes, if you want to store underwater, it is better to store in a solution which is saturated with lime, so that there is no external diffusion of the calcium. Okay. So, calcium leaching needs to be avoided in those cases. Now, in magnesium sulfate attack, this calcium leaching happens to a large degree. You form silica hydrate, and then this magnesium silica hydrate can combine to form what is called magnesium silicate hydrate, MSH, which is quite different from CSH. It does not have the kind of characteristics that CSH has. I will show you some images from the thing. Before that, of course, the modes of failure are associated with the expansions formed because of gypsum and ettringite formation that lead to cracking, and then because CSH itself is losing its stability, you have a loss of strength and integrity of the system. So, this is a picture from a column exposed to a sulfate soil, and this is exactly what we are talking about in the last class, where you have the major part of the damage at the soil air interface, and that is because not only you have a chemical effect here, you also have the Wick action, sorption, all those are forming a large part of what is happening to this system. So, most of the sulfate attack is characterized by a damage to the surface of the concrete. Obviously, sulfates are penetrating from the surface inwards, so most damage will be at the cover zone of the concrete. This is a case where the concrete at the cover has been almost completely removed from the system. So, you can see the rebar underneath, and the concrete has basically fallen away completely. The aggregates are intact, obviously aggregates are not participating in the attack, but the cement paste has been transformed into basically a non-cementitious system. Now, when you look at lab studies, this is from my own PhD work, so I have some slides from that. So, if you look at lab studies, general trends seem to indicate that there is some stage wise attack that is taking place, and most research that you find in sulfate attack will be related to sodium or magnesium sulfate, primarily from the viewpoint that these sulfates have the maximum solubility. So, if you want to do research on sulfate, you want to do it in a reasonable period of time. If you use calcium sulfate or gypsum or calcium sulfate to do your attack, then you will have to wait for a long time because you can't really put so much calcium sulfate into the water. In sodium and magnesium sulfate, you can make highly concentrated solutions. So, what the typical study involves preparation of mortar prisms and immersion inside a sulfate solution, and from time to time we measure the change in length of the mortar prisms. Okay. And this change in length is recorded with respect to the time of immersion, and in general what this tends to tell us is some sort of a stage wise process is happening in the case of sodium sulfate attack. In magnesium sulfate, it is a more gradual increase of the expansion. Okay. Now, what I looked at further when I combined these physical deterioration characteristics with the actual microstructural images from the system, what I was able to work out was some sort of a mechanism by which this damage actually occurs. Now, here this is your mortar which is immersed in a sulfate solution. The sulfate solution initially has a pH of 6 to 8. Okay. So, as soon as you put your mortar inside this 6 to 8 pH sulfate solution, there will be an outward diffusion of calcium hydroxide that leads to a increase in the pH of the surrounding environment to 11 to 12. Okay. And as calcium hydroxide is going out, there is some sulfate, sodium sulfate that is coming in, which is going to start depositing gypsum and ettringite at the skin of your specimen. Now, what is happening is the skin where gypsum and ettringite are formed is now starting to expand. Okay, it wants to expand, but there is an interior which is not attacked and it is restraining this expansion from taking place. Okay. So, what is happening as a result of that is that this resultant restraint to the expansion is leading to tension being created just underneath the skin, and the interior starts getting cracked. With time, this part which is having a lot of gypsum and ettringite starts becoming soft, right. Sulfates penetrate further in and start depositing gypsum and ettringite in this cracked zone which is at the interior. Then what happens next?
this zone starts to expand and then you have a cracking further interior to it and so on. So, this is a stage wise process. So, with this actually we were able to explain how mineral admixtures could be effective in the system, because when you form lesser gypsum and ettringite, when you replace cement with a mineral admixture, there is lesser tendency for gypsum and ettringite formation, because you are lowering the amount of calcium hydroxide in your system, right. When you do that, you are obviously causing a positive effect. So, the rate at which this progression actually happens to the inside of the concrete is reduced significantly when you substitute cement with mineral additives. Okay. Now, when you use magnesium sulfate solution, the effect is quite different. Of course, the same sort of thing happens in this case also. You have inward diffusion of your magnesium sulfate and outward movement of your calcium hydroxide, that leads to the formation of this double layer on the system. You have a gypsum and brucite or magnesium hydroxide layer forming. Okay. The brucite layer is stable for some time, but then all the inside reactions are still happening. Gypsum and ettringite formation is happening, which may again lead to cracking in the interior, because there is surface expansion leads to cracking in the interior. Eventually, the surface expansion will also fail the brucite layer. It will lead to cracking in the brucite layer, and your system, your sulfate will further penetrate into the system, again start depositing your magnesium related products and gypsum, and this is the kind of scenario you will get. So, in the previous one, you can see the surface zone, it is quite extensively cracked after a certain period of exposure. It is about 32 weeks of exposure to the concentrated sulfate solution, and if you look at the microstructure within that, you see a lot of ettringite in the pockets. If you look at this zone here, which looks like it has not been attacked, and if you look at the details there, you see massive deposits of gypsum. Okay, that means a lot of attack products have got deposited there, and especially if you go in a region around the aggregate, you see a complete layer of gypsum forming around the aggregate. Okay, and you have ettringite also, which is there inside the concrete. So, although it looks like this zone is unattacked, there is a lot of deposition of attack products that has happened in that zone. So, based on microstructural evidences and the way that the length change happened in the system, I worked out this mechanism which would explain the role of different kinds of chemical and mineral additives in the system. In magnesium sulfate, you can see very clearly at the early stage, after about 12 weeks of attack, you do not really see that much damage here in the surface zone, because you have a very stable layer of brucite, and just underneath that you have a layer of gypsum forming inside. But at a late stage of attack, you do not see that brucite layer anymore. You see the entire surface has been converted into magnesium silicate hydrate, MSH. Okay. And this is another case where the entire surface seems to be a mixture of MSH and gypsum, which is arising directly from this reaction that I showed you earlier. You get magnesium silicate hydrate and gypsum. So, this is almost forming in bands here, you can see in the microstructural study here, and that is what makes microstructural analysis of sulfate attack very interesting, because you get to see these features. If you look at regular concrete under the microstructure, it always looks the same. So, trying to figure out differences between two sets of concrete can be quite different and frustrating at times. In sulfate attack or any chemical deterioration, you see a lot of alterations to the structure, increase in porosity, deposition of attack products, which makes it very interesting to do this.